for the grid integration of green hydrogen energy systems. Okay, it will be delivered by Professor Jahangir. Over to you, Professor.
Thanks again, Dr. Animesh, and good morning, everyone. The first lecture, what I'm going to explain, I mean, although we did explain, like, you know, what actually mean by ancillary service, why we need pay more attention to deliver ancillary service to the grid with renewable energy, and most importantly with green hydrogen system. And then we can also talk about that how ancillary service is evolving, and then finally I am going to show a few examples to show the potential of ancillary service that can be delivered by green hydrogen system. Now, all of you already know that what actually we expect from power system, or as a engineer, if you want to design power system, I mean, what are the, like, you know, different aspects that we need to consider while we are designing, while we are operating the power system. So, as you know that, I mean, we talked many times that we need to decarbonize the power network, because this is one of the, like, you know, major contributor to greenhouse gas emission, and that is why most countries including Australia, India, now they are phasing out the fossil fuel power system, which is mainly comes from, like, you know, coal, gas and so on, by replacing with renewable energy renewable energy. Second requirement is that the system has to be reliable and resilient. So, the reliable and resilient means that we expect service 24/7. That means there will be no blackout, no outage of power supply. So, we expect continuous supply from the power system. That is mean like reliable. Other requirement that it has to be very high quality. The power quality should be very high. And again, as I mentioned, like that, power quality means we expect the current voltage waveform should be exactly sine wave, right. So, if it is not exactly sine wave, that means we do have power quality problem. And also when we have got, like, you know, voltage, frequency, like, you know, outside of the acceptable range, that also mean like that our power quality is not very high. And even that requirement is getting very tight with large scale renewables, and also when the system is operating very close to his maximum limit. So, for example, a transmission line has got, for example, capability, let us say, I mean, 20 megawatt, and it is operating and transmitting power close to that limit. And then, as you know that, I mean, the demand for electricity uses is going significantly as we are electrifying all other different sector, which are now either, you know, run by, you know, gas or, you know, other fuels. So, now we are moving more like electrified, even like the electric vehicle and so on. So, the demand is growing. So, we have to make sure that our system also, you know, upgrading, and at the same time also, I mean, we did mention that it has to be like economic, but as you know that it is having the sector coupling with other sector, for example, transportation, communication and so on. And again, also, I mean, it has to be like universal. We are not only considering, like, you know, few countries. So, we have to make sure that people from all around the world, they do have access, for that electricity. And most importantly, that it has to be affordable. So that's like the, more important even people in developing country where they have got like an economic constant. So those are the all things we need to ensure, and to ensure that in many of the cases that ancillary service can actually play a significant role to meet the goal that power system has, to supply power for the whole humanity. Now also we already talked about that while we are having large scale renewables, either Australia, India, or any other country, it's good that it is contributing to decarbonize the sector, but at the same time it is also introducing new problem, and new problems mainly again in terms of power quality, voltage imbalance, grid stability and reliability. And again, to address that issue, we need to get like an ancillary service from different inverter converters that use renewable energy in hydrogen in, and also other storage like batteries. So they actually should provide ancillary service to give that power quality requirement. Now we already talked about many times that is here, if like our frequency is 50 hertz, exactly like this, right, that means our system does not have any problem, right. So that means our generation, our demand are matching each other, right. But if it goes either left or right, that means we do have problem, right. And then we need to find out the ancillary service that we can get for any of the devices. And here many of the things that you can see, like photovoltaic system, fuel cell, wind turbine, many of the things can contribute to move that one either left or right. So this is like again already maintaining balance on sometimes difficult, but due to this this technology, even it's making to harder to keep that instantaneous balance between supply and demand. But still power system is inherently actually stable, because you see we always turning on and off the load, right. That means the demand is changing, but the system has got the capability to quickly make these things balance, considering all the control, all the monitoring system we have. So inherently is stable, but again in nowadays you see the frequency of blackout is actually getting higher due to not only large scale renewables, but also frequent severe weather events. Yeah, why we need that? We already talked about the ancillary service does help to manage the fluctuation in power demand as well as supply, which preventing grid disturbance and ensuring reliable flow of electricity. It does help to maintain the power quality, that means the voltage and frequency within limit. Ancillary service, that is also very, very important to integrate large scale renewables like wind and solar, and also even if there is an outage, that case also ancillary service black start capability that help to restore the grid and reduces the downtime of the grid. Again, there are plenty of different option that can help to integrate that variable large scale renewables. And here number of example provide. So it could be like that we have got very enhanced grid operation, other improved operation like different forecasting technique that I mentioned yesterday. And enhancing grid means either transmission, having new transmission expansion, or you are installing new devices like fax devices. Flexible operation, that's also actually quite important. And we did mention that once we have got those different control load, and one of the example that I provided, that electrolyzer. So when you can control many devices in the system, that means your system has got more flexibility. And once you have got more option, then it's easy to run any system, even like the power system, right? So even if you are organizing any company or any industry, you have more flexibility in terms of the people, in terms of the whatever devices you have in the system, then it would be more easy to run that system, same like in the power system as well. And then demand response, storage, and although all of these things like renewable are variable, but once you have got very accurate forecasting, actually you can address that variability option, because you already know what is coming ahead and you can just prepare based on that. And storage, previously we did have only few options, but now we have having more option once we have got the hydrogen as well. So that also helping to provide that service to the grid. Now in Australia, we have the organization which is called Australian Electricity Market Operator. They are the person who is responsible for ensuring that ancillary service to make the system more secure, more safe, and also reliable. And like in Australia, I think I found even I think in India, I'm not sure, I might be wrong, but they say like that in India you have grid controller or India Limited, which is probably responsible for maintaining the grid stability and reliability. So they might be the person who are providing ancillary service, and in Australia I already mentioned. So they actually mention and monitor that voltage, frequency, waveform quality, phase balance, everything are within the acceptable limit. If not, they are going to go to that ancillary service market and buy that operation to make sure that everything within the grid code and within their desirable range. Now when we are talking about ancillary service, it's like a set of operation. It's not like a single thing. It's beyond basic generation, transmission, and distribution, and that mainly essential for maintaining the reliability and stability. And here you can see there are so many example of ancillary service. For example, we even in the literature they classify into two different types. One is frequency and another is non-frequency. And the frequency could be fast frequency range, frequency control, regulator, fast frequency regulation. Sorry, I forgot it, but it's actually in the slide. But it's everything relevant to the frequency service to maintain that 50 Hz that I mentioned. And then the non-frequency, it could be related to the voltage, voltage regulation, reactive power service, and then other operating service could be that you have got that spinning reserve. If something happen, we could use the reserve service, and there are also a non-spinning reserve as well. And again, the other things that I also mentioned, black start capability, that also like sometime it consider under the under like the ancillary service here as well. So here things that I mentioned, sorry, that's like the things. First, frequency response, which is FFR. First, frequency containment service, which is FCR. That's I mentioned like in the previous slide, FCR. And then frequency restoration reserve, that FRR. So that's all, and even the inertia response, that's also relevant to the frequency. And then for voltage support, reactive power support, black start also, like which is called could be like a system restoration and different spinning service. But at what time frame you should provide what service, that also very, very important, right? For example, you see the inertia response, first frequency all are in the second, like, so it has to be very fast. When it's changing the frequency, whatever service is going to be, you need to provide like second to minute. So it will be like a fraction of minute. And then that is spinning service and other things that might be in the hour, reactive power and black start, that could be like in an hour to days. So whatever service you are planning, you have to make sure that you are providing that service considering the time frame that it needs. Because if there is a fast frequency problem and you are planning to supply like in maybe tens of minutes, by that time system will be already unstable. So you have to act very fast. And some of them like already, again this is that either automatic or manual, because that's already changing, right? Some of them like many of them might be automatic few years back, but every country now they are trying to go for like that is smart grid, where everything people are trying to make it automated. So some of them are already automated, some of them even not now, but it might be automated. And if it's automated, you see that time is quite fast. So again, most of the cases like either in second or even like the fraction of second, like the inertia, virtual inertia, and some of them, if it is manual, then you expect that it will be slightly like delayed service. Like here you can see like it is in the range of like a minute, which is like the manual. If you want to replace something manually, then definitely is going to take some time. But these are the different service, and this is the explanation of that, whether it's automatic or manual and what's the time frame. And the purpose I already mentioned, like to maintain the frequency and stability. Now this one just showing like, for example, let's say you have a power network and there is outage for some reason, either external fault or internal fault. Then what happened, like your frequency gonna go down, right? And then as you mentioned in previous slide, we have got number of action we take to bring the frequency back to 50 hertz, right? So again here you see that initially within few seconds we take some measure, and then if not, then we also have like other following service that gonna we apply to make sure that frequency go back to the previous condition. And here normally we call like the primary frequency control, secondary frequency control, and then we have got tertiary frequency control as well. Like one of them, the first one responsibility to make quickly back to the close, and then the following one to precisely making like 50 hertz. So for example, let's say it go like from 50 to 48, then we bring like close to 50. For example, let's say 49.5, and then the top level controller, they are trying to bring it precisely to 50 hertz. Like we already mentioned, like the supply and demand to make for the frequency control. Now in Australia, I mean we have got mainly that service are initially provided by AGC, you know, that automatic generation control. I think in India also quite same. In most country, I mean initial service are provided that on automatic gain control. And as I said that and that control also have like, you know, monitoring to see that, I mean the frequency whether within that range or not. And the normal operating band at all, this is the range that, you know, AMO always monitor and make sure that the frequency is within that limit. And how they actually do that service, again, I mean as I say, like, you know, they monitor, and then when like, you know, it change goes outside, they send that control signal to those like, you know, devices which provide ancillary service, and again check, if not then and then this is like a closed loop, and that's how actually they you know, do that frequency control service. And this is not only Australia, I think this done in India and other country as well. So that's the like, you know, AGC, but other one also, I mean as I showed in the previous slide, that contingency frequency control, which mainly you know, correct the supply demand following a major contingency effect, for example like a loss of generating unit, major industrial load, or large transmission event follow. But if like something small changes, AGC automatic gain control by automatically, I mean it can reach to the frequency. But this one will come into picture when you have got like, you know, very major event which will take the frequency far away from the 50 hertz, and in that case, I mean we need this sort of you know, service. So again, I mean this is the time frame when you have got this contingency frequency control. That's how you know, operate. So if you have like, you know, very fast I mean either, you know, going down or going up, they apply that service, and then you know, expect that it again, I mean slowly come back close to the, I mean 50 hertz. And as I say, like, you know, even if not 50 hertz, if one of the control cannot, then the top level control like, you know, secondary, tertiary, it will bring back to in the 50 hertz or close to 50 hertz. And there are that contingency frequency control that can be done in you know, not providing only single service. So definitely it's gonna coming from your generator. If generator not enough, you might have some load shedding, that, you know, you're cutting some of the load for balancing it. And also, I mean whatever the spinning reserve we mentioned, that you can have some, you know, generator which has got rapid service, you can also bring back to the system to increase the supply, so that it can be you know, matching with the demand. So there are, I mean number of, we actually we do provide that I mean emergency I mean frequency control service. And that, I mean regulation up or regulation down, I already mentioned that either it can drop or it can rise depending on, I mean if you have got generation outage and you know, your demand is higher than the generation, frequency will go down, and if generation is higher than the demand, frequency will go up. And again, I mean this is just showing, I mean different time frame where, I mean those, you know, fast raise of the frequency, if there is a drop, I mean we did mention provided in the frequency marker. So this is like the time frame for Australian national electricity market, but again I mean it could be quite similar, you know, for Indian case as well. Yeah, that's true. I think I already mentioned. And then that's all about like the frequency. What about if you have got the non-frequency, you know, regulation service that you need? And one of the non-frequency is important one is the voltage regulation. And we did explain like, you know, why voltage stability occurs. And then I mean if it occurs, then I mean somehow we have to make sure that like frequency, which is like demand and generation, but that's real power generation, I mean real power and real power demand. But for voltages, the reactive power supply and reactive power demand. If these two are equal, then I mean you will have, I mean your voltage is stable. Now here many of the voltage like, you know, is still like manual, but nowadays like, you know, OLTC and other things is getting like automatic as well. So the fax devices, that's also, I mean if you have, they, you know, operate automatically, but still I mean like the black start and other things, they done actually manually, because the system has got collapse and it's not that automatically. Then the whoever the operator, they will see like, you know, which devices they should start first, and then gradually which load it will bring online. So that's how, I mean they actually do it manually, but at the same time definitely they check the system performance as well. And voltage, like, you know, that instability, or you can say quality, that can happen in many different way. So you have got like normal voltage, and then you might have, you know, voltage interruption, voltage sag, under voltage, over voltage, voltage fluctuation. So it can happen actually in different way. It's not only going outside of the limit, but you know, that service can actually have, I mean, different types of problem. And again, I mean based on the problem also, I mean your solution would be different as well. For example, if you have got under voltage, it would be one solution. If you have got over voltage or voltage sag, voltage swell, I mean definitely, I mean you need different sort of, you know, service. Now for controlling the voltage, these are the like, you know, ancillary service. We have like, you know, voltage control ancillary service, network loading control ancillary service, and the last one, it's not exactly voltage, but it has got, you know, relation with the voltage, which is called transient and oscillatory stability ancillary service. Now again, I mean how that works. So as you know that every generator, it has got automatic voltage regulator. So when there is a change, generator try to absorb or generate reactive power to control the voltage, and as I mentioned that reactive power is managed actually to stabilize the network, mainly controlled capacitor and reactor. You know, the capacitor that can supply reactive power, and inductor, it can also absorb reactive power. So most of the cases when you are talking about the fax devices, it's nothing but the combination of power electronics plus capacitor and inductor. But also many system in a network also you find synchronous condenser as well. And again also other things, people are thinking that even in Australia, might be other country also thinking that when the normal generator retired from the system, because we are phasing out like the coals and other things, so why not we use that normal synchronous generator as a synchronous condenser. So that's not going to be producing power, but it can contribute to maintain the system stability and providing ancillary service. So that's Australia. They are already thinking that if they are retired and still they have got lifetime they can use, they will keep that in the network just to provide the ancillary service, but not to provide any even not for very long time, but still for few years, just to make sure that their system are stable. And then the transient and oscillatory, it definitely helps transient, but at the same time, as I said, that it also helps the voltages and so on. And one of the established devices control that actually help, you might already know that power system stabilizer, PSS. People when that we didn't have the renewable generator, and that time power system research was almost like sassued. People are mostly working with PSS and then AVR. But after that, when that renewables come, people are moving their research more to the renewable. But this is one of the devices that helps to improve the even small signal and transient stability. And this is one of the major component of the synchronous generator. And other devices that also can help, that synchronous condenser I already mentioned, SVC, that also, and also the devices which provide inertia support, even like the synthetic inertia that we mentioned, that also help to improve and provide like that transient and oscillatory and ancillary services. And then we talked about that black start or system restoration. That is also, you can think of like one sort of ancillary service as well. So once we have that either partial or complete system blackout, then we need that restoration service. And we already talked about that when we have got the grid forming inverter in the system with the green hydrogen system, that can help even for the system restoration as well. And for system restoration, definitely there are a number of stages. When we restore that one, so initially again you have to prepare and have proper plan how you're gonna do the restoration. And for example, let's say if the whole Australian grid get blackout, whether they're gonna, which city they're gonna bring first. So there would be like a location wise also map that that's how they're gonna do. They'll also plan which generator should be coming into the online first, and then how the other generator will bring as well. So once they have plan, then they restart that affected system and restore network and supply to the major generator, because many of the generator also like at the starting you might need supply to magnetize. Sometime if you have got a synchronous generator, right, if it is like separately excited, then you have to excite the system first as well. And then as I say, like how they're gonna bring the restore the load, how they're gonna bring the available generation, and then finally once they will also bring all the remaining customer transmission line, distribution line, everything online. So this is like in brief, but definitely when they plan, they have got like definitely established plan. They actually follow to do that. Now for like the green hydrogen, we already talked about like under what condition and how they can provide that ancillary services. And definitely also next lecture I'm also going to talk about some standard they need to follow when they are connecting in the grid as well. And although they are not participating in the demand both demand response and other ancillary service, but definitely they're gonna be participating in coming probably years. And once you can get ancillary service even like from green hydrogen and or others, there are like number of advantages, and one of them is that to delay the network upgradation service. So, for example, to delay the building new transmission line or distribution line. So, that like one of the major advantages when you can get ancillary service from the existing devices including hydrogen. So, this is like some of the existing project, like they are already doing experiment that whether hydrogen can provide ancillary service, and if like what sort of service. So, here you can see that number of them already like operational, few of them like in R&D phase, few of them like demo, some of them doing like feasibility study, but this is all real project, it is not like simulation. And this is some of the technology that they are using, and you see that most of them like PM, but they are using like others as well. And it is not only hydrogen, but you have got like other technology as well, other mostly like you see renewables, what the size of those like green hydrogen technology, and then what they are like end uses, what service they provide. So, all of them that I mentioned like an FCCR, FRR, grid balancing. So, and here also reference as well. So, in case if you want to go very deeper, like how like they are providing, and if you want to see some of the result that they already provided. So, what I am trying to say that it's not only idea, the technology is already available and some of them is already, but it's not like commercially providing, but once they say that it's like all the demonstrations successfully doing things, and at the end say that they find that this is also economically viable as well, because this is most of them their target to see that whether it's technically viable. But once it's done, then also you will do like economically viable as well, and once both of them are fine, definitely it gonna be providing great service to the grid as well. Although this is some of them, but as I said like we have got another class for standard, some of them for you already might know about those which is mainly using for renewable energy and also EMI and other things, but next class I am going to also talk about some of them as well. And for these are the some of the requirement, like in Australia they have already said that if someone want to integrate large scale electrolyzer or fuel cell, they have to do several study and make sure that it can provide all these services, then they are going to be allowing to connect with the grid if it is a large scale application. And I believe in Australia also you will be having similar requirement, just to make sure that it comply with all the regulatory requirement. Not only sometime also what happen like you have got state level, but also sometime you have got the country level, but sometimes also have the state level requirement as well. So, I think in India also Australia we have got different state, and probably you know better than me that every state have got their like own rules and regulation as well. So, that also sometime we need to satisfy, and it's not only like those grid requirement, but also in terms of safety, hazard. There are also many standard that we need to follow while you are designing and implementing those green hydrogen system. And even like, I mean, I do have experience, like even in our university we are trying to have a small kilowatt level experimental setup, and it took almost like year, I mean, to have that lab ready, because they are also invited external expert. They come and check, because they have got very strict requirement, and I believe here also if you want to do that, so that's why you have to start probably taking like at least 1 year time, that if you want to develop a good lab. So again, it's not like everything from my paper. Some of them I have taken from the literature. I do have like one example from my group as well. So here, like one of the case study done by the research group from NREL in USA. So they are having like good setup, to do both like hardware in loop experiment, and also the doing experiment with the comparatively small size system as well. So they are doing both simulation as well as experiment, just to see like what sort of service they can provide, because although we are talking more generalized frequency and different type of stability, but it's not that every time you will be able to solve that problem using hydrogen. So if something relevant to the demand side, the load, the electrolyzer, one of the examples that you remember that I shown previously, so that can actually provide good service. But let's say if some problem introduced by synchronous generator, for example, if you have got a small signal stability, in that case it is found that the electrolyzer, it cannot contribute to reduce the oscillation that's coming from the synchronous generator. So that's why we need actually more research to find out exactly like if you have a system, if problems can happen in different area, right? So it might be that something relevant to photovoltaic system, might be something from synchronous generator. So it's not that if anything's happen, you expect that the problem will be solved by the green hydrogen system. So that's why we actually need to do like more studies, to see like what problem exactly it can solve and what problem it cannot solve. So here they did simulation with that system, and if you want to parameter, actually it's given in that paper as well. But they did a study with like considering different situation. For example, let's say that so initially they consider load loss. That means like I think 50 megawatt of the load, actually they are disconnected, and when load disconnected, you expect that the frequency is going to rise, right? And here also they are, because in USA frequency 60 hertz, frequency have rise. But the thing is like that they did consider that without any electrolyzer, and then considering like 0% DR, 25% DR. So again, what it says that EL frequency response. So what is it does? You have designed a control that when the frequency changes, your electrolyzer will respond. But if you don't have any control that with frequency, like the power coming to the electrolyzer, then actually it will not respond like that. So here they do have that frequency response service, and then they consider like different level of DR, like is it 0%, 25%, and also 50% in both cases, with and without electrolyzer. And they, for example, let's say if you have got 50% DR with an without electrolyzer, what frequency reduction it can make. Same for like if you have got 25%, like what sort of frequency regulation actually you can provide. So here both like in one cases load gain, and if you load gain, then you will also find that frequency gonna decrease. But again, like the similar things, like when it is rise, the service that is provided, when it is lost, can they provide like a similar sort of service? And again, so when the load losses, that means what electrolyzer gonna do? It gonna reduce the power taken from the grid. That's how it responds, right? And with the load gain, more load coming to the it will be in a opposite way. When the load demand rise, they're gonna reduce the input power. So that's how the generation and balance will demand, right? And in other cases, it's actually opposite. So again, this all the service is happening by only changing the input power coming to the electrolyzer, because you have got the control that when the frequency changes, the power taken by the electrolyzer will change accordingly. And this one, like what about if you have not load change, but if you have got, let's say, like a temporary fault, it could be that for a certain period of time, you have got either short circuit or whatever, and then the the fault is removed, then how the system is responding, again quite similar percentage. So the reason they did that, because they want to understand exactly, like when they're going to implement in the system, like how much service it provide, and then what sort of technology they need, what sort of control probably they can provide, and so on. Anyway, I have got actually two more examples, but I think again probably I will just skip due to the time limit. So this is like one of the projects that we just started in our university. It's given like the objective mostly like controlling voltage frequency, and then we did get some result, but here just only one thing that we did two sort of simulation when you have got like the instability itself in the generator. So the generator is actually have got the transient instability problem. So here you can see that you have got three generators, like so one of the electrolyzer is close to that. So what happened when there is a fault, this generator become unstable. So this electrolyzer, it means to provide, it bring back to stability, but it could not remove the frequency oscillation from the system. So what it means that you need additional control with the electrolyzer. So only electrolyzer is not enough, to remove all problem that you might have in the system. So like how we design those sort of control, and when you have got also like here the problems that we found in one of the Australian system, that during very sunny days, due to the power coming from photovoltaic system, they got like the over voltage problem. So by using electrolyzer, we could see that how we could remove that problem, and using what sort of electrolyzer, what margin of the voltage they can actually change in the system. And also I did have one example with MPC controller as well, but I'll leave it to for you to read and see. All the step is also given. If any of want to, we all also discussed in the previous class as well, but it showed that in certain condition, both the combination of droop control and MPPC, it can actually provide better performance. So it does compare with many cases like the PID, and then virtual inertia control, and also the MPC in the secondary level or the primary level in the droop, and then it compare like which one provides. So definitely the MPC and the combination of the droop, it found that it can actually provide better performance when you have got the large disturbance in the system. So yeah, so these are the some of the again like the challenges and more opportunities probably. Again, I mean, if you really want to work in this area, you can have this slide and see that where actually you can contribute, and then you can also, I mean, interested, I mean, you can develop some project and go on from there. And as I said like previously, I'm always more than happy. This is all the like the last day, but it's not the last day for our contact. You can contact anytime later as well. I'll be very happy to give whatever recommendation I can give it from my experience. Thank you.
Thank you, Professor. So we'll keep the question after the next lecture. We'll take 5 minutes quick break and we'll start the next one.
Yes.
Percentage of DERs what you wrote, 0%, 20%, it is penetration of DERs or a connection of DERs?
It's a penetration of DR. then you have break, right? After. So lunch will be here, or we have to go same place? No, it's okay.
Okay, welcome back. So we will be starting the lecture number 14, which will be on standards, policy, health, safety, protection, reliability, sizing, and seating associated with the hydrogen technology. This will be delivered by Professor Jahangir again. Over to you, sir.
Yeah, thanks again, and welcome back. So here, this lecture is nothing like technical. All the information is publicly available, and I'm actually not working any of the topics in my research group. So, but still, I'll try my best. I mean, to explain what I have learned, by reading some online material. So here you can see that it does involve number of things, like the policy, standard, health issue, safety, and how we can protect like the different devices, worker from the danger that it has from like or it can produce from hydrogen technology. And then what are the different sizing of the technology available in the market, and their seating as well. So let's start with like what like the people's perception about that green hydrogen system. So one of the like study done in Japan, and they asked like initially like in the left hand side, you can see that how much you do actually know about this like falling energy technology. And the answer option is I know it, I have heard about it, and I have never heard about it. So if you think like the hydrogen, only 20% people actually they know about this technology. Another 43% they have heard about it, but they don't have any knowledge about this technology. And 30% they even had not heard about this technology as well. So I think in terms of knowing about this technology, you can see that like solar, wind, they do have like people have better knowledge about solar, wind than hydrogen, and that actually makes sense because hydrogen is comparatively, mainly the green hydrogen is comparatively new technology, right? I don't know about like in Australia or India, like how many percentage know about hydrogen technology. I don't think it would be like even 20%, right? People might heard about it, but knowing about this technology, only people who might be like interested about doing some research or doing business or making some investment, they probably know about it. And the student might be who are studying chemical engineering, electrical, mechanical, they might also know about it. But what I'm trying to say that actually we need to do more work, to deliver the message to the community, and we also need to have like workshop discussion so that they heard about the technology, and not only hearding but also they know about this technology as well. So again, in terms of like more details about the hydrogen, what they are finding. So they're asking like whether hydrogen is harmful to human or not. Is hydrogen lighter or heavier than air? Does hydrogen smell or not? Is hydrogen inflammable or not? Does hydrogen need other energy to be used as energy or not? But here also you see like I don't know, I mean it also depends the cohort. I mean they conducted the survey, but I believe this is survey more like people who already know about the hydrogen technology, unless they can't answer, right? But even it does, many people does not have, I mean real understanding about like the hydrogen property, about like safety feature that I mean you need. So I mean in those respect also, I mean those of us like working in the hydrogen, also we need to do further study to know more about the other aspect of the hydrogen, not only the hydrogen utilization, but while we are utilizing, how we can ensure like safe operation of the technology and also for the operator people who are using. So we need to do further study, because in many cases what happen, we are always interested the area that we work. In most of the cases, I mean if something comes which is not relevant to us, we just ignore it. But actually it's a good idea to know pros and cons of any technology we use. So this is one of the like 3-dimensional framework that people who are working on that social science and things like that, they use like to provide like a structured way to understand how society interacts and influence the adoption of hydrogen. So here you can see that there are like 3 components here. One is socio-political acceptance, another is like a community acceptance, another is like a market acceptance. And depending on here which whatever the point you are, it will tell you like here this 3 party how the acceptance level like here. So this sort of approach they use like to gather those information regarding safety, acceptance and so on. Now what actually characteristics that hydrogen fundamentally different from like other conventional fuel like gas and gasoline and natural gas. So these are the like characteristic of the hydrogen which is quite important. So hydrogen is colorless, probably you already know, is odorless and also lighter than air. So this is actually very, very light, even lighter than air. It disperses quickly when actually it releases, and that's how the safety is also quite important for hydrogen technology, and it's really, really highly inflammable, flammable, not flammable. So if something happen, it's quickly, even with a small amount of energy, you might get fire. And also it has got quite wider flammability range from like 4% to 75% in air. And as I said, like a low ignition energy is required, meaning even a small spark can ignite it. And because hydrogen flames are nearly invisible, so detecting a fire visibility can be very difficult as well. So that's also another aspect. The safety things also we need to take it very seriously when we are working with hydrogen, because it's not visual. And what actually makes hydrogen like so much dangerous? So that's few of them I already mentioned. So, these are the things that high flammability, low density, wide ignition rates, high diffusivity, odorless and colorless, that actually makes hydrogen more dangerous than other gas. Then these are the property, and it does mention like why it is dangerous. So, high flammability means that it ignites at low energy and burns with an invisible flame, that is I mentioned. Low density means it escapes quickly and increasing the risk of leaks. And wider, we already mentioned 4 to 75%. High diffusivity is spread rapidly in the air, making leaks hard to detect. And as it does not have any color, sometimes also it's very difficult to identify leak without having any sensor. So, in those cases, I mean people are working, they actually use very reliable sensor with this technology as well. So, the sensor required not only for doing different measurement by measuring different signal, but also for safety reason also people use sensor here. And here again as I say, like the explosion, fire, cryogenic burns and material incompatibility, that are the different safety hazard that involved with this hydrogen technology. Now, the first one, as I say, like the fire. So, the fire, the cause is the hydrogen is extremely flammable, that I mentioned. It ignites easily even with a small spark. So, unlike natural gas or gasoline, hydrogen burn with an almost invisible flame, making it really hard to detect, and this actually increases the risk of unintentional fire in industry and laboratory setting. So, that is why we need better risk assessment and safety level even in the lab as well. And this is giving some of the facts, like it ignites with, as I said, like very small parts. So, it's even only need 0.02 megajoules. So, it's even a milli, so it's like a fraction of millijoule that can cause a fire. So, you see like what sort of a small energy actually that can cause a fire. And flammability is, we already mentioned, 4% to 75%, making leaks highly dangerous. And the color and noise, smell and color, that also makes things more difficult as well. The second one, like the explosion. So, it does not only cause fire, but it also cause like explosion as well. And it can occur even, as I said, like certain amount of hydrogen accumulate in a confined space, and an ignition source is present. So, if like small hydrogen accumulate in a confined space, and in case if there is a ignition source is present, it can actually produce explosion as well. And here even a tiny spark can trigger an explosion. Hydrogen air mixture between 18 to 59% concentrate can actually do that detonate. Fast flame progression, hydrogen flame travel at actually very high speed, and that actually increases damage if mainly say like a enclosed space. Material incompatibility. So, hydrogen can also make certain material weak and brittle, leading to produce cracks, leaks and equipment failure, where hydrogen atom penetrate the metal surface and can cause structural damage over time. So, if you have got like an stainless steel and aluminum, while that regular steel and iron could be vulnerable, in case of pipelines, storage tank, valves, that must be designed with that hydrogen resistance materials. And equipment exposed to hydrogen for long period also can crack and break unexpectedly as well. So, that is why this sort of hazard we need to take it seriously. So, other thing, I mean, you already know that hydrogen can be stored like gas at very high pressure, or even liquid like at very low temperature, and also like solid as well. But when the liquid hydrogen is stored, this like you see that it minus 253 degrees centigrade. So, making it like one of the coldest substance on the earth. And what can happen if you have that sort of like cold things, and if it comes like in contact either your skin and eye, it can actually cause several tissue damage, and also it could be like in your skin as well. So, it can damage as well. So, it is not only like fire and a very high temperature, also like we have to be careful when we are dealing with the liquid hydrogen as well. And these are the facts. I mean, it can freeze human tissue, I mean, within second. Metal surfaces exposed to liquid hydrogen become prone to cracking as well, and that is why we need proper personal protective equipment, including gloves, face shield, if you are really working and doing experiment with different forms of hydrogen. And this one just compare type of explosion that can happen. One of them is faster and another one is a little bit slower, but that actually compare whether it is speed is less than the sound or faster than the sound, but both of them actually quite dangerous. So, I probably just skip this one. So, these are the some of the characteristics of the detonation which I mentioned, that high speed explosion with shock waves. So, the flame front can moves at like 343 meter per second, which also sometimes reaches like very high speed as well, and that can actually create a shock wave, and that can cause actually severe structural damage as well. And when it is actually stored like in a confined space, like an inside tank or like a closed industry facilities. So, that type, I mean, this sort of dangerous things can happen as well. These are the some of the symptoms, like it could be the hydrogen level like low, moderate, high, and what could be like the health effect. In the low cases, I mean, it might be no immediate effect. If you have got like the moderate, where oxygen is below that level, because that hydrogen does use oxygen. So, in cases if there is a leak or something like that, the oxygen can go very minimum level, and that can produce like headache, dizziness, and sometime it might be like the loss of consciousness as well, which can bring like potential fatality as well. So, we need to check the oxygen level. I mean, if you work in a very confined space with hydrogen. So, that is why you already mentioned that there are sort of different health risks involved. It either you have got gaseous or liquid or even in a confined space. So, and all of this then can cause different level of accident and injury as well. So, if you compare the burning speed of hydrogen with others, you can see that the hydrogen warp speed is very fast, while actually spread very rapidly if you compare with natural gas, gasoline. So, you can see this is like only 0.4, wherever this is like almost 3.5. So, it is really high if you compare it with other gases. And this safety level is not only like in one section, it could be either in the production, it could be either storage, or even it could be in the transportation as well. So that's why I mean the safety level you need for all cases. If you work either production or storage, or even somebody in the transportation sector working with the hydrogen vehicle, in all of the cases there are safety challenges, and we need to take appropriate measure to reduce the risk. And here if you think about hydrogen production, these are the few processes. We already explained number of processes you can use, like while you are producing hydrogen, and as usual the electrolysis, we said this is one of the like widely probably utilized method that will be coming in the future, although not now. So if it is electrolysis, the risk could be relevant to electrical, because we does use electricity coming from different electrical sources, and also thermal and explosion risk, and this can happen either fault, overheating, gas leaks, or even electrical arc from electrical arc as well. And then steam methane reforming, as we explained, this is one of the method which use very high temperature, while this is a very low temperature, but this one actually it is very high temperature. And where you have got high temperature, if something happen, you might have the flammable gas, and also the toxic carbon monoxide as well, which is quite dangerous for our health as well. And then the other method, like either biomass and also the byproduct we are getting. So from that also there are some health hazard as well. What are the protection you can take to either minimize or completely remove? So you could have explosion proof enclosure, and very intrinsic safety design, considering what sort of safety level you have. Based on that, that there are safety design as well. Redundant pressure and temperature sensors, so that you monitor exactly what the pressure and temperature currently working. Automated emergency shutdown system, so if anything happen, the system will shut down automatically. Also you need to routinely test leaking, and also you should have real time gas detector as well. So in the room, if anything leak, it can automatically detect that there is a gas, and then based on that you can take an immediate action. You should also have proper ventilation to prevent gas accumulation. And then for designing hazardous area, this is some of the standard people use. So while we are doing this production area, probably we should also comply with this one and also other standard we have as well. So even in the either university or other level laboratory, also we need to make sure that we comply the national level different standard, and also university health and safety protocol. So this standard, as I said, that's actually mainly classify area where you have got explosive atmosphere, and that can occur to ensure the correct selection of electrical and mechanical equipment. And also for hydrogen production, there are different level of zone, and based on that you have to take an appropriate level of risk. And it says zone 1, zone 0, zone 1 and zone 2. So zone 1, an area where an explosive gas atmosphere is present continuously for long period or frequently. Here atmosphere like to occur in normal operation. And zone 2, an area which is not likely to occur in normal, but if it is occurs, it will exist only for a short period of time. So depending on that, definitely for zone 0, you need to take very highest level of risk, because here as I said, an explosive gas atmosphere is present continuously for a long period of life, or it might happen frequently. But in other cases, risk level could be high and moderate, and based on that, there are some relevant example is given relevant to hydrogen. So it could be that this one zone 0 could be inside hydrogen storage tank or electrolyzer enclosure, which is relevant to like zone 0. Area near hydrogen pipeline compressor, that relevant to zone 1. And if we have got well ventilated room like housing hydrogen equipment and outdoor hydrogen dispenser, so that is zone 2, which is again like well ventilated, so already protected, but still there is a moderate risk. And then like generation, even for storage also you have got safety challenges, because storage you already know that we store in very high pressure compressed gas, very cold compressed, and also recently we are also doing like solid hydrogen storage as well. And this is like different sort of number facts. We already mentioned what sort of pressure we utilize, what sort of temperature, right? So as we have got very low, very high pressure, and sometime the devices we use also utilize high temperature, like that the high temperature mainly for the production, but for storage like high pressure and very low temperature, that's the mostly two hazardous area for storing hydrogen. And here again it has got different type, like type 1, type 2, type 3, type 4. So type 1 like the cylinder, which is like used like different like the metal cylinder for storing hydrogen, and then type 2 like load bearing metal linear types of material normally used for type 2. For type 3 non loading bearing metal, and then for type 4 also like different other materials as well. But again I'm not expert on those different types of material and their characteristics, but in any cases if you know like about those like vessels and other things, but it is given here and also given online as well. If any of you want to work in the storage hydrogen as well. And for storage also it can cause sometime leakage. You might have like high pressure rupture, like failure of tanks or fittings, that can cause like violate explosion and other health hazard. So in those cases also we need to take that safety challenge seriously. Here also like some other risk for liquid hydrogen, that we mentioned very like low temperature, even like solid state storage, also like thermal runaway toxicity. These are the two risks that we need to take if it is storage like the solid, and therefore like there are some even for storage there are some mitigation measure that we can take, like pressure relief valves, and then hydrogen sensor real time monitoring, ventilation system, vent stacks, and mostly like type 4 composite pressure vessel with layered containment that give like better safety level. And also we need to do like periodic test. We should also maintain safe distance as well. And then for also transportation, there are risks because we do use like onboard like hydrogen, and if any accident happen, it also got health risk as well. So the hydrogen is transported not only used in the vehicle but also transported pipeline, tube trailer, different tankers, chemical carriers like ammonia and so on. And if you have like a pipelines, sometime Pipeline also might have like technical concern related to the pipeline transportation transmission. So whatever like we material we use, if there is a leak, then I mean probably it could be dangerous and whoever living close to that particular area. Here I mean there are some like potential solution that can be utilized to ensure that there is no leak from the pipeline transportation. So you can use like this sort of material which has got been a better safety rate for hydrogen distribution. And then if you have got the tube, that also like hydrogen compress like this sort of tube at very high pressure. And again I mean if there is something happen here, this is also like have got severe health hazard as well. And there are some accident already happened. It's not that it didn't happen. So there are already some incident happened due to those transportation issues. And here is mentioned like for pipeline and other type of things, what are the risk, whether it's leak, whether it's toxic exposure, and there are like relevant to hydrogen, what sort of risk, it is a high risk or it's a small risk. But in any cases, I mean we have to take that transportation issue seriously. And this one mentioned like for the overall transportation, what sort of mitigation measure you can need. So you can use like use of hydrogen compatible materials, inspection like all of these cases regularly, pipeline leak detection system, isolation valves. Like we should also have better training that if any emergency cases happens, how we respond, and GPS monitor transportation and pressure logging. That also might help even to make it more safer. Now that's more like what are the hazard and safety level. Now there are some standard already available, and people are also working with like different standard. And you might know that standard are defined like as a set of available rules. They define products, system, and process. They also set out some testing requirement. They also enable trade, measurement, and quality checks as well. So all of this like mentioned in the standard. Now in Australia, we do have like standard Australia. Also India, you do have like standard India. So they are some sort of organization with who they work with like different independent non-government body with different national standard. Also they have regular contact with international representation as well, and they do have trusted partner with government, industry, and also the border community as well. So this sort of standard is quite standard, and even for hydrogen you will have this sort of body within that standard. They do regularly see all the things that can happen. So as I said, they do have regular meeting with different body. They develop different proposal and standard. They do have like technical working committee, and they also sometime regularly they also ask for public comment as well. So when they have got any things released, they ask comment from different body even to improve their standard. So this is the normal process how those standard develop, including even like the hydrogen. So after completing all the process, they will finalize and they will publish and make it public so that anyone can actually utilize that. Now in Australia, we do have like one hydrogen standard development structure. So here you see that they have got like 3 different body who are working with defined spec, and they are also having number of people. They do meet, and that's how probably they're gonna have probably very massive final level hydrogen standard in coming years. And this again I mean mention like some of the benefit while we are adopting international standard. We do have that international standard for in other cases like defined network, renewable energy and so on, and same for hydrogen also. I mean once you adopt those standard, it's going to reflect the experience of industry regulator worldwide. It's going to facilitate the international certification scheme. So those of like industry who are doing business, for example, if they develop a product here, the certified by Indian authority, but they sometimes also take certification from international community organization as well, so that they can sell the product not only their home country, but also for to other country as well. So as I say like that, the health hazard depend on different part of the hydrogen value chain. So that hydrogen standard Australia, they are actually developing one hydrogen standards tool, and that actually do involve all of them, like the production, transportation, blending with other gas network, truck transport, hydrogen refueling station. So they do incorporate all that hydrogen value chain. I mean to ensure that they actually do consider everything. Now here some of the things that I mentioned here. So it's not only for Australian, but some of that it is quite common for other country as well. So for example, this one it dealing mainly with pressure swing adsorption system for hydrogen separation and purification. So this is more like hydrogen separation and purification, and I'll lead you to read that scope, what actually it does involve, but again this is mostly relevant to hydrogen. Then this is another one which is also relevant to ISO, maybe probably you already have heard about, but this, although this is Australian, but it's actually quite compliance with the ISO. And even the previous one, it also complying with that ISO TS standard as well. And this is more like electrolytic hydrogen production. So this sub standard is mainly relevant to the production, and then hydrogen generator using like electrolysis for industrial, commercial, residential application. So if anything relevant to that, it's actually given like in this standard. This is more like again production, but this is more like the standardization of the test method for hydrogen production, mainly for hydrogen purity level. So that's to analyze that, they follow this like standard, and here you can see that it does involve number of things, which is we talked about when we talk about the different chemical reaction, that all of these things are involved in the hydrogen production. This is more like the hydrogen storage. So one of them more like design, construction, testing. The other one mostly like the pressure vessel storage, that is mainly relevant to that one. So and you can see the corresponding standard, title and also scope are given. So later if you see that you are involving any of them, you can see which standard actually directly relevant to your work, and then you can go and read the details in details the standard. And then some of them like like cylinder storage, hydride storage, pressure vessel storage. So again, I mean, depending on which storage, there are like corresponding sub-standard as well. Then more like the hydrogen transport, like how you are transporting hydrogen depending on that, either cylinder or tube. Then based on that also, there are some hydrogen standard available, but you will see most of the standard is still like they are like ongoing. It's not like that they have already finalized everything, but still, I mean, you will get enough, if you mainly doing the like the research level. And then this one more like the pipeline transport. So pipeline transport also, I mean, there are some relevant standard, and also you can read what like their corresponding purpose of those standard as well. Next, blended hydrogen. So if you want to blend hydrogen with the other gas network, then what sort of standard you're going to follow. And also, I mean, you can see that for either blending into natural gas pipeline, in some of the cases also like there are some difference. So you will find those, I mean, this from I mean different given standard as well. Then hydrogen refueling station, because in Australia, as I said already, there are number of hydrogen refueling station. So they do have good standard. I mean, that how you gonna design, how you gonna operate, how you gonna do the maintenance. So there are some corresponding standard also given for refueling station as well. So here are some more standard for hydrogen refueling. Then the final two topics, as I said, like the seating, one of them. So the hydrogen seating, like the decision, I mean, where are you gonna put your hydrogen, green hydrogen system. So there are some key criteria that might help, like to decide the hydrogen seating. So this decision will actually impact definitely the cost, safety, environmental compliance, and also public acceptance. So you need to consider all of them. So for example, the factor that you need to consider, as we're going to use from renewables. So is it like proximity to renewable energy sources? That going to reduce the transmission line losses and grid congestion. As we utilize water, what sort of access you have to for water, and that's mainly critical when you're going to utilize the electrolysis process. Safety distance, like whether you have got safe separation from people. So if someone living some area, how far your system from those suburb and the area that people are living. And then zoning and land use. So also like you must comply with local state regulation and planning scheme. If you are using land in a particular zone, that also you need to consider while you are thinking of setting up hydrogen infrastructure. And then also transportation logic, where your hydrogen gonna be utilized, right? And also where you are generating, how you gonna transport, what sort of mechanism you gonna use it, that also you need to consider. If it's always better if it is close to the end user. Also if you have got good access with the road, rail, ports for hydrogen distribution. And then environmental impact, always I mean you have to avoid the sensitive ecosystem. I mean where you are thinking of that seating hydrogen infrastructure. So these are the some of the specific infrastructure consideration you need to take about. If you have got like the hydrogen hub, pipelines, refueling station, and storage. So again, probably this one is very self-explanatory. So we can just read, while you have got time. Then sizing, this sort of like different sizing criteria, that what should be like electrolyzer capacity, what sort of storage tank you are going to consider for storage, fuel cell or gas turbine sizing. So if you want to calculate like the electrolyzer size, this sort of like equation you're gonna utilize. So this is like quite simple equation that based on like the demand and so on, actually you can find out what sort of electrolyzer capacity you might need for your particular application, what's like the volume and pressures that needed to find out your storage tank sizing, and this one your power output, if you have fuel cell, what sort of power you gonna give, either you design for a either house, for industry, for agriculture application. So the kilowatt capacity, you will be easily able to find what of the sizing fuel cell you need for that particular application. So again, I hope that's not that boring, because as I said, this is nothing technical, and for me as a technical person, I don't know how I can make it more engaging and type of lecture where everybody can enjoy. But the thing is important that you know like where you can go if you want to find particular information. That's the main motivation for this lecture. So again, you don't need to read every day. Based on your interest, based on your application, everything is given in the slide. Whenever you need, you go and read it. Thank you.
Thank you, Professor. So here all the lectures from Professor Jahangir is coming to end, and we'll take 5 to 7 minutes question, then we'll go for high tea. Any questions? Even a previous lecture, if you have any question, you can ask now.
Also, if not, while we are taking tea, I'll be there, so we can
Yeah,
talk.
so tea will be ready in 5 minutes, so we have 5 minutes
Okay,
time.
okay.
Okay, anyway, so let me then announce that all of you are aware of exam, right? So 1:15 to 2:15 is the lunch, 2:15 to 3:15 is the exam, and then we'll close the ceremony. So for lunch we have arranged, you have seen the transit facility. So when you take a turn to hostel, don't go there. If you take straight, it will be transit facility. So lunch is ready, so you just need to go and help yourself, okay? And I think we are still waiting for 5 minutes. The things will come, and all of you will get the certificates today, but transcript will email you after we check your exam. So based on the grades, we'll fill the transcript from our institute and we'll email you individually. Okay. So some credits will be also be given for your exam. Okay. So so I hope all this lecture from Professor Jahangir is somehow useful, because we started from the very fundamental of difference between a fuel cell and a hydrogen electrolyzer. So I believe that at least that difference you know and leave this course, because many people confuse with fuel cell and hydrogen electrolyzer. Both are not same. And from that aspect, again we go to the power electronics interface details that requires for the electrolyzer for giving a power supply. And finally today and yesterday some part we started discussing the microgrid application and also some grid integration application. And today was mostly the standards, codes, safety design. And Professor gave the previous lecture mostly a overview of ancillary services, what we say. So after the break, I'll have also my last lecture, which I'll be mostly discussing a particular grid code, which which is more popular in transmission level for grid integration, and that is applicable for all IBR, whether it is solar, wind power plant, or even battery. So that is called IEEE 2800, and that I will be giving you an overview. And you will have, because for particularly hydrogen grid integration, there is no standards yet come up. Whatever professor told is mostly at the hydrogen level, safety standard, and some of the thing at the chemical level you maintain. But when you say hydrogen at grid scale and those integration, there is no specific rule is there, but people are working more towards developing or revising the existing 2800 grid. So I'll give you a hint of 2800 so that you know that what is required. If you are a developer, if you have a big solar power plant, you want to integrate to the grid, let's say Indian grid. Indian grid, we have the grid code is prepared by the Central Electricity Authority, as you might know, CEA guidelines we follow. And any renewable plant you want to integrate to the Indian grid, you have to make sure that you all those power plant, what you develop follows the guidelines, what professor told, whether it's frequency, whether it is voltage, whether it is, kind of protection regarding islanding or anti-islanding, all these things. It not only you develop your power electronics or develop your system, but you have to follow the guidelines to be integrated with the existing Indian grid. So yeah, we'll have now break and we'll be back in maybe 10 minutes, and then we'll start the last lecture before lunch. Thank you. slides are there, so some slides I have to go fast, but definitely I will summarize the slide in 2-3 lines, but I will again share the slides after the talk. So as I told, one line I want to say here in very layman language, if a lot of resources are there in the grid, or let's say for example in a classroom there are so many students. If there are no kind of rules or regulations how to maintain a classroom, definitely there will be noise, right? Yes or no? That's why every starting from school level there are rules and regulations. All the students from maybe play school level to the evening university level, you have so many rules and regulations student has to follow to be adhere to the guidelines of the respective university. So why I am saying that grid is, you can say, university, and you have all these renewable energy sources, loads, reactive power compensators, all you can consider as one students with a different background. Now existing grid has only synchronous generators, right? Now they have already built some kind of rules for themselves. Now those synchronous generators are leaving. Now all these new non-fossil fuel based power generation are coming into the modern grid. Not only in India, it is all globally also. Now to accommodate all this behavior, because renewable, wind, battery, even hydrogen, all have their own characteristics, right? And grid has its own characteristics. So all of them have to be on same page, right? Now to maintain the discipline in the grid, what I say, discipline in the grid, so all of them have to follow some kind of rules and regulation. In power system language we call it grid codes, okay? So grid people already developed a set of rules and regulations, and they have classified the rules and regulation depending upon the nature of the incoming power source. If it is a renewable, if it is a battery, if it is a load, depending upon, you have to have a set of codes, and those codes are already drafted in terms of some kind of standards, okay, which is many of them are publicly available. Now having said that, in our perspective, grid codes are required. When I say inverter based resources, those resources can be renewable, wind, and anything else, okay. Now what I am going to show here, this development of grid code and technical requirements I will go through very quick. So again I told, while preparing the grid codes there are different stakeholders are involved. It is not only grid people who will decide on their own zone that this is the set of rules all the generating plants need to be followed. So the stakeholders can be system operators, which we say, let's say in Indian case it is Indian grid people, generator suppliers, let's say developers who generates the solar PV power plant, and the consumers, because at the end of the day, if you are connecting a renewable power plant to the grid, already existing consumers also should not be affected. So having the discussion among these three or maybe sometimes more stakeholders, all these guidelines in terms of grid codes have been prepared, and also they have taken into consideration of the variable renewable generation, which might impact the total amount of generation profile in the grid. So what are the technical requirements is already discussed, I will not go much, but these are the most, I mean, you find out any country grid code who have already established, whether it is Germany, Australia, India, even European grid codes. So all of them might have different scale of measurement, but the philosophy behind the grid code, how you maintain these disciplines, okay? You connect a renewable power plant, how much voltage and frequency operating zone you should operate. Frequency control capability, so Professor Jahangir already told some are frequency related, some are non-frequency related. Non-frequency related are mostly the voltage related. So all the things are related to voltage or frequency, how you maintain when you connect to the grid. And again those maintaining the frequency or voltage in two mode, because sometimes grid goes to steady state mode, sometimes grid exhibit some kind of transient disturbances, for instance fault. Okay. So, depending upon that, the grid code sometimes classify this same behavior in case of normal operating condition, in case of abnormal operating condition. So, frequency and voltage ranges are different. When you have a steady state condition, system is very smooth, running very flat state, but when the fault happens, that time the grid does not want you to behave the same way as you are behaving during the steady state. There are certain changes you have to include in your operation or in your plant controller. Okay. Similarly, active power, reactive power, all are active power, let us say related to frequency, reactive power related to voltage, and this relation only exists in case of transmission system. Okay. So, these grid codes, what I am going to say are more stringent or more strict at the transmission level. Okay. Distribution level, they can relax some of the grid codes. The transmission level, when you talk about let us say megawatt scale power generation or load, and that you want to connect a transmission level voltage kilovolt level, those time small disturbance would also be create big hazards. Okay. Sometimes it result into pure blackout. It has been already observed in different parts of the globe. For instance, Australian blackout, we have a Mumbai blackout also, and we have also several blackout in US, like in 2016-17, 1200 megawatt solar power plant went off due to some kind of fault. There is another 900 megawatt solar power plant in same US also went up in 2017. So, from all those experiences, this now this grid people have come up with very strict rules, so that before you finally connect your plant to the existing grid, you make sure that you pass all the tests. I mean, you have to tick mark all the tests offline or some kind of high level detailed modeling and simulation you have to show the grid utility people. They have to certify the okay, so your plant is following all this. Now you can go ahead and connect on field. Okay. So, before that you have to make sure that you follow all of them. So, now there is a slight difference between ancillary service and grid codes. Okay. Ancillary service, if you see my scale, particularly this curve. So, here my x axis I call it as a capability curve, and y axis I call it as a service curve. Okay. So, the positive x axis I have put capability must have, a renewable power plant must have this capability. The negative towards that more it is might have or may have. Okay. Similarly, service it must deliver, y axis, service it might deliver in the negative y axis. So, you can see my first quadrant is more important, because here you have to have a must have capability and must provide service. So, what are those? Mostly your primary control, active power control, reactive power control, fault right through, these are like abnormal voltage condition. You have a fault happens, how you ride through the fault. Then power quality, what we discussed, some voltage quality you have to or current quality you have to maintain, and then some kind of ramp limits again, because you inject the active power, but there is a way your active power injection should, rate of change of active power, that slope should follow, that is basically the ramp limit of the this thing. And similarly this curve, if you see the lower one and upper one, mostly there are ancillary services which are mandatory and which are optional. Ancillary service, when I say some ancillary services are optional, where if you provide by your renewable power plant, so grid will somehow give you some kind of benefits. Okay. Let us say frequency services, I will give you an example. Frequency services by renewable plant can be different. If you remember Professor Jahangir's lecture, there are fast frequency regulation, primary frequency regulation, but here the primary frequency comes here, which is a must ancillary service. Okay. But there is something called fast frequency response, which is required during the transient disturbance, where frequency suddenly drops. So, you have to fast respond to that frequency change. So, that is one of the what I say, not mandatory, but if you can show that your plant is capable of even responding to that fast frequency, then grid people will appreciate and give you some kind of benefits. So, there are different tariffs are available even different countries. Even India also, if you provide fast frequency service from your renewable plant, then you will be benefited. So, this is basically a brief one slide depend about what are the services and capability you should showcase from your renewable plant when you go towards integrating to a grid. Then this is my main focus of this lecture. So, it is called IEEE 28002022. So, it has a second version come maybe 3 months back. So, the newer version is 2022.2. So, you can check online, they will be get the guidelines. So, 2800 is a grid code, is mostly applicable for the renewable power plant integration at the sub-transmission and transmission level. It is not applicable for the distribution level renewable integration. Distribution, if you some of you might have known, mostly for microgrid or distributed energy resources integration, we follow that very popular IEEE 1547. But this is particularly sub-transmission and transmission level, and this is a, you can say, IEEE standard. It is not, I mean, it is open to every country. So, it is an international grid code. Okay. Now, apart from this grid code, as I told, every country also have a some kind of country related grid code, depending upon their network infrastructure, system infrastructure, how the system can behave if you connect, they create some country grid code. So, depending upon the utility operator or grid operator's point of view, they will tell which grid code you have to follow, whether their own country grid code or some kind of international grid code also you can follow. Mostly this kind of international grid code are being followed by the academics or researchers, but actually for industry people, they have to follow mostly this country specific grid codes, okay, because they have to actually go and they have invested some money, they have to go and actually install the megawatt level power plant. Okay. Now, the scope again, as I told, it is written in the second line, transmission and sub-transmission system. Okay. So, all this reactive, all this comes, I'll go through that, and this is, there are certain definitions also they have given in the grid code. Okay. So, if you see, this is my grid, what I call a transmission system. Okay. There are 3 definitions you have to understand for grid integration. So, mostly people confuse with or take commonly everything as point of common coupling, but IEEE 2800 specifically defines three connection points. First, they call something called point of intersection, POI. When this square box, if you see, that is becomes a plant. Okay. When I say plant, it is not a single solar inverter. It's a combination of, you can say, this is a IBR unit, this is also IBR unit. So, there is a bunch of IBR units. Then you have some inverter transformer. Then at the end you have a very high voltage transformer. Then total power plant you connect to the rest of the system through this breaker. So, this point is called point of interconnection, POI. And 2800, all 70% of the standard or rules, they apply with respect to point of intersection. If something happens here, how you should behave. If voltage falls here, how should behave. If frequency falls here, if islanding happens here, how you should behave. This is a breaker. Okay. This is a main breaker where you connect to the rest of the grid. Now, this is your main transformer, this is a collector branch. Collector branch means a bunch of IBR units you connect here through different breakers like parallel connection. So, this plant you can say is basically a megawatt level at the transmission scale, and the voltage you can say this can be your maybe this will be basically your normal single unit, 690 volt you can take, 690 to maybe 33 kV, and this can be your 33 to 66 kV high voltage transformer. Okay. This is the central transformer where all you connect, then pass the power to the this thing. So, apart from point of interconnection, there is also a point called point of connection, which is basically the IBR terminal. Okay. So, if you see IBR unit, this can be solar, this can be wind, this can be anything. So where that connect to this transformer, that means you can see the exactly inverter terminal. Okay, maybe if it is a string or central inverter, that point where it connects to the low voltage side of the inverter transformer, that point is called point of connection. Okay, so there can be multiple point of connection for a plant, but point of interconnection should be one. Are you getting? Any questions so far? So here also you can have different types of supplemental control. Let's say we are discussing, let's say, reactive power compensation. You want to connect some STATCOM or something at the high voltage side of the power plant, because just to help the reactive power either inject or absorb during the requirement. So you have a breaker. Let's say because you know it, let's say STATCOM, it doesn't contribute any active power. So you can switch on when the reactive power requires and switch off when it is not required. So you can use here, and there are, so this is basically a bunch of more wind and solar you can connect, but at the end this is the rest of the system. Okay. Yeah, so this is basically a very generic layout you should understand, because before going to more into the document, these definitions, point and identification are important, because these standards or many grid code, country code standards is mostly not written by technical people, mostly written by lawyers, some kind of non-technical, and their languages are very complex to understand. So that's why graphical understanding of this picture or layout is more important to understand what they want to mention in their different clauses. Okay. So this is called a SC connected inverter based resources. Okay. Now next they have a specifically given for a type for wind turbine power plant. So they told that there may be different HVDC link connected inverters, and those point of connections also they mentioned. So when they refer in the document something for wind power plant, and they will mention that with respect to the point of connection. So you will understand this is the point of connection. So this graphical illustration is very much important to understand or read the standards or grid codes mentioned in 2800. Okay. So so this RPA called basically the point of applicability. Okay. So that is equal to your point of intersection, means every standard in the document they refer to this point, reference point of applicability. Okay. If you read the document several times, you will come across if voltage falls 50% at RPA, that means you will refer voltage falls here at 50%. Okay, because RPA signifies the point of interconnection point. So I am just giving you a brief how to read the standard. Okay, and in detail you can read once you understand these things. Getting? Yes. Point of measurement, where it is? This one? This is default. So what happens sometimes, this both can be actually RPA, but RPA means this both can be point of interconnection. But sometimes what happens, your IBR connection point and your the rest of the grid point, there might be some kind of HVD high voltage line. If the line exists, grid people will tell you which to take as a point of interconnection, whether the HV line this side or HV line that side. You understand, this is your HV transformer. Sometimes exactly at the transformer secondary you connect to the grid, but sometimes they give you this much length of high voltage line you have to lay down, then you connect to the grid. Someone asking how to calculate short circuit ratio, right? Grid short circuit ratio, there it comes, like this is your grid and how much line you facing before you connect to the grid. So that line impedance plays a critical role deciding whether it is a weak grid, strong grid. Okay. If you have like weak grid means you have impedance is very high. Impedance is very high means electrical distance is very high, right? So short circuit ratio is inversely proportional to your grid impedance. So this is your, you can say, grid impedance. Sometimes there might be very little grid impedance, so that this point and that point you don't see that much voltage variation or active power variation. But if it is significant distance from your connection point to this utility point, then you have to consider this line, and they will tell you consider this or maybe this, which one to take. This is grid people will tell you when you do the study. Okay. But this point of measurements you will be informed. Being a a developer, renewable plant, power plant developer, you will be told that take this point as a reference of point of measurement. Okay. Yeah, another thing, in this grid code you see several dynamic rules and regulation. Let's say, so they gave a very common picture, like if your system, if your IBR power plant controller sees a steps, sorry, any question? If your power plant control in any of the signal, whether active power, voltage, frequency, reactive power, any of the signal, it faces a sudden step change. This green you see, it is basically the control reference. If your controller sees a step change, your plant should be follow this dynamics. So there are different, mostly terms are related to your control system, rise time, settling time. So one of the things they call reaction time. Reaction time means you give a step change, you wait when your plant starts responding to that step change. So this much very small distance is called reaction time. Your plant reacts to that change. Then after that, till you reach the 10%, not 10%, till you reach the 10%, they tell it some time. Then from 10 to 90% they call rise time. These things you know from control system. And there is a band, you have to band of operation, like high percent, low percent, they will also mention. So we are discussing how to design a controller. These are the thumb rule you have to follow. Whatever you do, how much fascinating controller you design, how much making non-linear, linear, at the end of the day response should be this much, or this is called optimum response. Okay. So all these values, rise time, step response time, when you go to the inside more and more into the document, these values will be given for each clause. If frequency falls, they will give rise time should be this. That means you should refer to the definition here. What is rise time they mean here, they mention. Understood? I will tell here.
Sir, what is this input step, like as a frequency input, like?
Can be anything. I will show you. I will show you. There are several. I showed you na, there are several things you have to follow in the grid code, and those things you have to follow in steady state and follow in your abnormal condition also. This is mostly to be followed for steady state.
And sir, next is that this input is coming from the transmission side to the.
I'll give you that picture. So what happens? Yes. How I'll draw. So basically, if I go to the previous picture here.
Yes, sir.
So this is all your plant, right?
Yeah.
And you know all this, maybe some are like grid following, forming, whatever. They require some kind of active reactive power references.
Yeah.
To control the active reactive power injection to the grid, right? Now, why they tell this is your reference point? So you will take a line and measure the active power, reactive power in that line.
Yes, sir.
And from this point you measure the voltage and frequency. These 4 parameters: active power, reactive power, voltage, magnitude and frequency.
Yes, sir.
Those things, there will be a something layer, it is not there, something called power plant controller, PPC we call that. That is a very high level control that controls all the IBR units. So all the tertiary control what you Professor Jahangir was discussing of forecasting, optimization, that happens in that controller. So sometimes it is linked to the SCADA, or sometimes it like operate alone, like a digital control. PPC we call power plant control. So this all measurement, because this is a system measurement, right? All after you give it to this all measurement go to that layer of control PPC. That PPC different kind of forecasting, optimization, demand response things happens. Then new power P and Q generated based on optimization. How much this guy has to inject P and Q after optimization, doing the generation demand at the tertiary level. Now, once that is decided, the what is this much P and Q, if you provided by this IBR, it can do the converging load flow, steady state operation. So that power reference has to come through each and every one.
No, so I'm getting it, but the question is that is the disturbance coming from the transmission side, and how this thing is reacting to that? The graph is basically.
Yes, I am saying that. Let's say your initial active power reference for this IBR unit is P1.
Okay.
But suddenly some changes in the system happens, maybe in steady state.
Okay.
The PPC decides for this IBR unit you have to change to P1 to P2.
Okay.
It might be P1 plus P2 or P1 minus P2. So that has to be steady state. It will give you some time. Within that time, reference will change.
Okay.
Then once the reference change, you have to follow, your controller should follow that reference,
Okay.
following these dynamics. Your
Okay.
rise time should be this much, settling time should be this much,
Okay.
over should be this much, and your band of operation should be this much. Okay. And that step change is not related to only power. I told you it can be voltage, frequency, reactive power, active power, anything.
So any change in the IVR units,
Yes,
those
yes,
are
yes.
should be within these.
Yes,
framework.
as I go through the slide, it will be more clear
Okay.
when I go a particular event. Okay, so I told you about this. So basically, when I say reactive power control, this is one of the control required for steady state operation. You know, in transmission level, reactive power is related to voltage, right? Now, what happens? So before reactive power voltage is basically a PQ capability. Some of you are like, some people are from CPRI here. So they know every power plant you have to follow that PQ capability curve. Like your plant should ensure that for a certain range of P and Q, we can, dispatch your P and Q, right? So what this grid code says, if I take the x-axis as active power, y-axis as reactive power, so this is your ICR, this means the rated active power of your power plant, okay? This is the 10% of your 10% active power of your power plant rating, okay? So they tell when you operate between 10% to 100%, you should ensure your Q injection or Q absorption should be 0.3287 times the P. What is the power factor? Power factor will be tan inverse Q by P, right? Yes or no? So, though you change your active power in this zone, you keep on dispatching 10%, 20%, 30%, 100%, your reactive power should maintain this much minimum. You cannot operate below this. It is not it will be said you are not compliant to the grid code. Minimum reactive power should be 0.3287 times that much whatever you are maintaining. So this is, let's say, my 5 megawatt. My plant is 5 megawatt. So this is my 5 megawatt, and 5 megawatt times 0.3287, that is my Q mean. Or if it is a battery, it can also observe, that is my Q mean in the negative Q. Okay. So that you have to maintain. If you maintain and show that, this is a steady state operation, right? You are running load flow, you change your active power slowly, step by step, and measure your Q. So if you fulfill that all the things, then you tell that, okay, my plant is PQ capability curve is matching the standard. Okay. So that is for active power injection. For instance, if I have a fuel cell inject or absorb active power? Inject. So it can be fuel cell. But if it is an electrolyzer, it is a sink of active power. It has to follow this, because active power is negative here. This is your 0 point. So if it is consuming active power also, from your 0 to 100%, you maintain your Q this. Okay. So this is for who are generating active power, this is for who are consuming active power. For battery it is both, right? Charging, discharging. So you have to maintain PQ first, that is first point of check whether you are capable of connecting to grid or not, because transient disturbance fault are very momentary. You have to stay connected with the grid for all kind of steady state zone. So in that you have to maintain this. Okay. So more things you can find from the more exact details you can find from the document. Okay. I just tell you that this is how they see your power plant performance before connecting to the grid. Okay. Yes. And your plant is also big, it is a combination of IBR units. So as a whole plant you have to maintain this. They are not asking for a single inverter.
Okay.
So you saw this, right? When I said if the active power this much, it has to be measured here. So you can see so much contribution active power.
Okay.
They can decide from power plant control, if you don't have capacity, they will do the optimization. So you should not overload. So they will decide that, but as a whole plant, they will do the test here.
Okay.
They will measure the P and Q. They will disturb the P from 10 to 90. They will measure your Q and check like you can say table wise.
Yeah.
Okay. So that all included, but at the end of the day, at the POI, that standard should be followed.
Yes.
Okay.
Yes.
Now this is another check. While providing that much Q, how much voltage you should, because once you change the Q or you maintain that much Q is minimum that, but if you let's say you can also provide more Q if required. But what is the level of voltage at the RPA? When I say RPA, again I will go back to POI, right? So at that point, how much voltage should be maintained? So there are different points are there, V2, V3, V4, and there is a table here. If your RPA voltage, if they measure the voltage of your plant connection point is less than 200 kV, your V1 point should be 0.9. So they have mentioned all the coordinates of the x-axis. Okay, that means if you are running at 0.95, your RPA voltage is 0.95, you maintain the reactive power that much. But let's say the point you are operating somewhere between 0.9, because 0.9 to 95 is itself a steady state, right? So 0.9 to this point, this is steady state operation, but it doesn't mean you always operate at 1 per unit. Sometimes you operate between 0.9 to 0.95 per unit. So if your operating point is in between, so your reactive reactive power curve can follow this black line. It need not to be again 0.3287. It can follow this slope. At 0.9 you can maintain 0.7 Q min. Okay, got it? And that coordinates of x-axis can vary depending upon the voltage level at the RPA. If it is less than 200 kV or between 200 and 500 or 500 or 735 kV, all are transmission level voltage. Okay, so that voltage level you can check. So basically in that PPC you have two control, one is active power frequency control, one is reactive power voltage control. So based on the reactive voltage measurement, you do the reactive power voltage control and give a Q reference to your plant. So that Q reference while you give, you have to follow all the standard. You have to see where the voltage operating point, and that time you select that Q reference from the plant controller, you give to individual IBR units. Okay. So this is bit of, I am going fast, I know. Some students it is very high level. Yeah, question? Yeah.
When voltage is like 0.9 pu, shouldn't we be injecting more reactive power?
Which one?
Like 0.9.
This one?
Yeah.
No, they have told that depending upon the system stability, because this curve and previous curve has to match. So all are to be coordinated. So by doing more Q, you should not sacrifice P. So P is more important. Q sometimes you can manage with a little bit, but that's what, like P, Q, V and frequency all are coordinated, though they cannot be totally decoupled. Though they control the at transmission level, they tell P is mostly influenced by frequency and Q is mostly influenced by voltage. But the moment you change Q, because your plant capacity is fixed, right? The moment you sacrifice with or you try to inject more Q, you have to sacrifice your P. You cannot overload your plant, right? You might overload 20%, 30%, but again you have to take care of that. That should not be exhausted unless until very much needed, and that is needed during abnormal condition. And what we are discussing, steady state. So steady state, you try to inject more active power. Okay, so that is what they prepared. I mean, these values again I am telling only refer to 2800. If you go to different grid core country, these values might change depending upon their grid infrastructure. Okay, so yeah, so that whatever the PPC control I told, power plant control, active power control, reactive power control, two things happens. In reactive power control, you have three modes. You can control the voltage with respect to reactive power, or you can simply control the power factor. Power factor control means you have to maintain a particular power factor. To maintain that, if you are changing P, you have to changing Q, because power factor equal to tan inverse reactive power by active power. So your power factor, if you are running on power factor control, so if there is a set power factor, you have to maintain that, whether by if you are changing within the power factor, if you are changing Q, you have to adjust P so that net power factor remains same. Okay. Apart from that, there is a reactive power set point control. So you have a set point decided from your plant person. They will give you a signal to the IBR unit. Okay, this is your set reactive power now. You have to follow that. Okay. So this all controller, again I am saying, is not at the single IBR unit. It is a plant level controller. Okay. IBR control on all we discussed yesterday. Following grid forming, internal voltage current, those will be going on. But being a plant, at the plant level also you have to maintain these things, because at the end of the day you have to inject P and Q at a stable V and F to the grid. Okay. V, when I say voltage, F is frequency. Okay. And yes, while doing so, remember they will simply give you these values. But how to measure this, they told you in the graphs. Let's say they told reaction time for all these controls should be 200 millisecond. Okay. Let's say your reactive power set point change. Okay. So reactive power set point change means that step change happen. So your plant should respond within less than 200 milliseconds. That is your reaction time. Then for other things, are let's say damping ratio. For a system, damping ratio should be maintained 0.3 or higher. If they see that your damping response is less than 0.3, then it is not compliant. Okay. That's why they have given table to each type of clause. Okay. And all this rise time, definition, reaction time is mentioned in the graph, which is they put in the introductory page itself for the reader to understand what is the reaction time, rise time. Okay. This is reactive power control mode, and the other one I told active power frequency, right? So active power frequency means my x axis is P, y axis is F. If I change something in F, so basically this is not a, is this a directly proportional? This line, is it a directly proportional? Can I say F is directly proportional to P? It's a droop curve, right? Inversely proportional. That means if you are injecting more P, your frequency will decrease. And this line is 50 Hertz for India, Australia, and US it is 60 Hertz. Okay. Now, with respect to this line, this upper side is over frequency region, 50 plus or 60 plus, the lower side is under frequency region, right? But they are telling there is a dead band between the lower frequency, under frequency and over frequency. So that deadband also they will mention in the grid, utility people will tell you. So they are telling if your frequency is somewhere in between this region, okay, if your frequency is somewhere in bit region, so what should be your active power? This is 0, right? This is 0. The curve starts from here. The curve starts from here. So in order to maintain stability, they tell for small frequency variation, whether over frequency, under frequency, you don't bother about pumping more active power, because their system might get unstable. But when you cross these dead zones, in the over frequency they called dead band over frequency dBOF, dead band under frequency dBUF. If let's say your system frequency, again when I say frequency, it is at the POI point, not inverter terminal point, POI point. If it goes above this or goes below this, then you have to follow this red curve. There is a slope of this red curve, that is KOF. This is the slope of under frequency red curve. That means if you are here, so you have to maintain this much active power, because frequency is this much. Okay. For under frequency also same, like over frequency and under frequency. Okay. Now this is called primary frequency response. This slope of this curve, they told it can be vary from 2 to 5. 2 to 5 slope of this curve. Slope is basically delta F by delta P, right? Delta F by delta P, delta Y by delta X. That should vary from 2 to 5 for primary frequency response. It is less, less turbulent or less or slow, you can say. But I will show the next curve, something called fast frequency. Same curve, same slope, same curve, same relation, but slope will be different, because slope decides how fast you inject. So primary frequency 2 to 5, they have given a flexibility, grid people, you can maintain anything in between that. This is an example again how to decide. So if your frequency, they have given a formula, you can check the document. For low frequency zone, you have this KUF, which is the slope of that curve. F nominal, you know, this is your measured frequency. Till you cross dead band under frequency, no injection, they measure the frequency deviation after you cross this under frequency. Nominal minus the measured frequency minus dead band, because till dead band no P equal to 0. So after this measurement, they will compare whether your maximum value is 0 or this. Whatever value comes, they will add to the value at rated value, we can say pre disturbance value. So that much again they will calculate whether your availability is there or not. With under frequency means you have to inject more power, but if you are running already full capacity, you cannot inject, right? Where you will bring? So they check. If it is you are running at full capacity, they will tell, okay, whatever this calculation comes, don't bother, you give your full capacity. Let's say you are running, your plant is running at 50% capacity. What you do, whatever comes, you check whether 50% capacity is more or they require, let's say 70%. So you step your 50% capacity to 70% to help the frequency. This is what we call frequency ancillary services, helping the frequency. So here electrolyzer can play a role, because electrolyzer can control its active power consumption, and when it is required, if system grid requires that time, right? If it is under frequency event, it will consume more power, or over frequency, you will do the opposite. There is also a high frequency calculation. If you see this KUF, KOF, the slopes. Sometimes they are equal, sometimes the utility people purposefully give you some value because they know what is going on in the system. Okay, the slopes might be equal, may not be equal. Okay. This is again what you maintain. As I told, this slope you can vary from 2 to 5, but default value is 5. If you are not able to maintain 5, they can give you a relaxation. You can maintain 3, 4 droop slope, percentage you can say. For over frequency also same. Now this deadband, how much it should be? If it is a 50 hertz, it is 0.06% of 50 hertz, the deadband. Till your frequency is within that deadband, you don't inject any active power. But it crosses up and down, you then follow that red curve I show. But again, this is default. You can have a relaxation between 0.025% to 1.6%. Okay, getting bit fast, right? I know because we are restricted to time, but I am okay. I am open to discussion. I will also share with you the slide along with the standard. So you read that and read our see our slides. If you have any question, you can just contact me. Okay, but this is very interesting. It is very fascinating how this grid, very complex grid of India is operating, and suddenly in that you are pumping some renewable power. So it is like a jerk to the grid, but that jerk should be smooth. Otherwise, anything can happen because Indian grid is very complex and very big. Okay. So what I am telling this because all these clauses may be applicable to hydrogen electrolyzer because it is also a controllable flexible load. Okay, or even fuel cell which can be a flexible source. Okay. So all this because for grid integration we have to follow this because that is also transmission level. So these are some theory you can read. I leave it to you. So this is basically a fast frequency response already discussed by Professor Jahangir. So what happens? Something happens, frequency suddenly jump. So this frequency and this difference, we call it as a frequency nadir in power system language. What is the delta F? We call frequency nadir. And the way it drops, if you measure the slope, that we call rate of change of frequency. So during disturbance, when the rate of change of frequency is very high, if you don't have fast frequency response capability, your system will trip because the moment it jumps, you cannot respond by your active power because your system doesn't have flexibility to react that much fast. But even if let's say you have this FFR, then you can get rid of this. So instead of going to more unstable without FFR, it can recover. Okay. It can recover slowly. So this is the arresting period, which is basically captured by your FFR or fast frequency response capability. If you don't have this curve, instead of going back, it will go to more and collapse. System will collapse. And that time, your active power, that red curve slope, it has to be 1%. That is mandatory. 1% means is very aggressive. Sudden change in frequency, it will react fast, so that you can arrest the frequency here. Then with the help of secondary frequency control, you can recover the frequency slowly to the system level. Okay, that's why fast frequency service is a recommended service, but not mandatory, because this type of event doesn't happen frequently. This happens, let's say this sometimes very high short circuit fault happens and you see this kind of very high rock off. Rock off means your df by dt is very high. Change in frequency with respect to time, that we call rate of change of frequency, rock off. And the frequency deviation we call frequency nadir. I am telling this terminology because you will get along with this when you read the document. Okay. Yeah, so as I told, different types of frequency control are there. Frequency primary, secondary, this zone you see, tertiary will. Now tertiary time your optimization algorithm again will play in role. It will see whether you need to disconnect some load or connect some load, so that you bring back your frequency to post pre-fault level. Okay. So this is period is also not mandatory, and they have a very high time. You can see 10 minutes onwards you have time, but this time if you see, it is a number of seconds, 10 seconds, 5 seconds. Within that your primary frequency in terms of FFR should act. Then 10 minutes onwards till 10 seconds onwards till 10 minutes, you have this time to recover the frequency to activate your secondary control. Then after that, when you reach somewhere here, your tertiary control comes into picture. It will do the generation demand balance. Then you go back to your frequency. Okay. This is what I told, some example for FFR calculation. It is very simple. They have given an example in the document. You can go through that. They have taken here 60 years because it is an IEEE is international US based organization. Okay. Yeah, as I was telling, this is 1%. Okay. This is mostly they prefer 1%, but if sometimes because you have invested a lot, you have to actually, to be very honest, negotiate with the grid people. Okay, I am fulfilling everything, but this I am not doing. So they will give you some kind of conditional compliant, but you have to inform that you are not doing that. Okay. So this is actually, rather than technical, also so many, what I say, consulting things are involved. You have to convince grid people for certain things. Again it comes now abnormal voltage disturbance. I will skip this voltage right through. When fault happens, voltage, if you see in the curve, it jumps from 100% to, depending upon the fault magnitude. Because fault happens, your voltage sag will happen, voltage magnitude will drop down. Then if you see in the curve, there is something called mandatory operation zone for certain time. If you don't fulfill that, then it is not compliant. So fault right through meaning, classical meaning is, if fault happens, generally what happens, to save your plant you disconnect. But right through, English word means you stay connected, you wait for the, you ride through the fault rather than disconnecting. They have given, you need not to stay connected for longer. There is a specific x-axis time. If a voltage falls for this many magnitude, for this many time at least you stay connected. That quality is called, or that functionality is called fault right through. Okay. If still fault happens after that, you trip. Grid people will tell you trip. Okay. So there are different things are there. We don't have time to go much into low voltage right through, because when fault, basically low voltage happens, right? And sometimes when you switch some capacitor and all, you may face some high voltage to right through that times, high voltage. So you should also maintain high voltage right through. And when fault happens, first check is you ride through the fault. Then second check is, being connected, you inject more reactive power rather than active power, because voltage is related to what? Reactive power, right? When fault happens, suddenly it is abnormal, it is not within steady state, your voltage operating point will suddenly jump. So your reactive power injection should be very high to help recovery the voltage. So that's why they tell, while connected, if you can supply the reactive power to the grid, it will be helpful for the grid to recover the voltage. Yes.
So there is a question. Suppose if there is a 4 grid at the generator side, and we are fulfill the grid code for the LVRT. We fulfill the code of the LVRT. So where is our measuring point, at whether there is a PCC side or POI side?
No, this voltage measurement point is POI. But
POI.
That is a good question. As I told, injecting reactive power. Inverter, each IVR unit has to help in injecting reactive power. So how much reactive power each IBR will inject, that has to be calculated from the inverter terminal voltage. But this voltage, whatever the curve I showed, that is POI voltage.
Okay. So we have to provide the additional reactive power support at the generator side if the
Yes.
fault is there.
Yes.
Okay.
But important question is, important catch is here. This curve I showed, let's say my voltage falls to 40%. 40% at the POI. But do you think 40% the inverter will see?
No, it will not, sir.
Because you have lines, transformers, all has to be added up. That then whatever your inverters see. That is a big research topic or some kind of discussion going on, because we are facing issue in Rajasthan grid complex. What happens? All these in power plants are tuned to respond to fault based on POI measurement. But sometimes what happens, at POI your voltage follows, voltage tell you to follow right through. But when you reach to the terminal, you are still at steady state point. Let's say I am exactly at this boundary point. POI voltage, let's say some 89%, but still it is fault right through, right? 90% is this line. This is 100% continuous upper the steady state.
Yes.
Below that is your fault. If I am running my POI voltage at 89%, and somehow your line total system losses and everything you add up and you see terminal voltage is 91%. So being a IBR, I see I am running in steady state, but being a plant, I am in fault.
But sir, in this case, we have to fulfill the reactive power requirement, I think below 0.16 seconds. Then and then we can achieve this
30
characteristic.
milliseconds.
30 milliseconds.
30 milliseconds.
Then and then we can achieve this
Yes.
characteristics.
That is one thing. But my question sometimes, what is the real time issue? Because when fault happens, you don't listen to PPC. IBR will not listen to PPC instruction. IBR will activate its fault right through control. So PQ reference it will take from a fault right through controller. So what happens? IBR, when 89% voltage sag, the plant requires you to inject reactive power, but at the inverter you see voltage is 91%. So that misunderstanding between IBR unit and the plant, there is some oscillations in the reactive power what Rajasthan grid is now facing due to the renewable solar power plant integrations. So now they are telling how to estimate exact voltage drop at the terminal, because this is not terminal voltage, this is POI voltage. Okay, so research are going on that. So I think we are done. I'll share with this slide. So basically at the end of the day, this is your inverter power stage and filter. Okay, this is your controller input, and the outside the blue color all you see whatever we discussed. So this is all. So if you can achieve all these things, this inverter power plant can call as a grid code compliant inverter. Okay, and you can see this predefined set point, measurement, priority selection, all are coming. Then this is continuous mode, normal operating condition, PQ capability, QB control, PF control, then right through, fault right through, low voltage right through, high voltage right through, all has to be. So this will tell you which event is going on. It will give a mode selection, whether you want steady state, fault, whatever. Then based on the mode, this will give you control signal to the inverter. Okay. All right, 5 minutes you have, and here we end all the lectures for this 5-day program.
So,
Thank you.
Thank you, Dr. Animesh sir, for the valuable presentation. So, any further questions from the audience?
Or we'll discuss in the afternoon after all things over, because we are getting late. So you can head to transit facility. Lunch is arranged. So please come sharp by 2:15. It is less distance only. You have seen, I think, the transit facility.